Hi and welcome everyone to an Australian Water Association webinar. We're very lucky to have Rick Stover from the United States here to talk to us about semi-batch reverse osmosis for water quality. I'm just going to do a very quick introduction in terms of any technicalities that might pop up. There is a number in that text box at the bottom left-hand corner that contains a number to call if you have any audio or visual problems. That number is available throughout the entire presentation, so you'll be able to contact someone at Redback if you are having any issues. At the end of the presentation, hopefully there'll be a bit of time for Q&A, and if Rick is willing, he can answer some of your questions. Also, if there are any other issues, please don't be afraid to pop them in the text box, and I or someone from the tech team at Redback should be able to help you. I'm going to hand it over to Jerome Mullen, who will do a quick introduction of Rick, and then it's over to Rick.
Great. Good afternoon, everyone. So just a quick introduction about Rick. Rick Stover has over 25 years experience working in the water industry with both commercial and technical experience and a focus on water treatment efficiency. As Desalitech Executive Vice President, he is responsible for market strategy, customer and technical support, and growth of the company's leadership role in reverse osmosis water purification. He previously served as Chief Technical Officer and Senior Vice President of Marketing for Energy Recovery, the leading supplier of energy recovery devices for seawater desalination. He then joined Osmosis Water, where he developed forward osmosis processes. So please welcome Rick Stover. So Rick, over to you.
Well, hello. It's a real honor and a pleasure to be working with the Australian Water Association and you all. My roots in desalination and water treatment are in seawater reverse osmosis, and my first big project was the desalination plant in Kwinana in Western Australia, the Perth plant, in 2005, and had the honor of working at a number of the desalination plants in Australia. Since I've shifted to what I'll be talking about today, which is Desalitech, and our focus is actually on brackish and industrial water purification and treatment. But I also serve on the board of the directors of the International Desalination Association. Okay, so switch off my camera.
Hi Rick, you might need to put your microphone back on.
Thank you for that prompt. Terrific. So thank you for the introduction. Sorry about the pause. And as stated, I'm serving as Executive Vice President for Desalitech. Desalitech is a company focused on commercializing a new reverse osmosis process. So we're using standard reverse osmosis equipment in a new way, and I'll talk about that. The company's been around since 2009. We have commercial installations around the world that have been operating since then, mostly focused on brackish and industrial water treatment, purification, desalination and purification. And there should be plenty of time at the end of the talk, so please note any questions or comments, and very happy to entertain those. Right, the reason Desalitech is in business is because the world is running out of conventional water supplies. Surface water and groundwater are drying up or becoming increasingly contaminated. In the developed world, like the United States and Australia, industrial industry consumes the majority of freshwater resources, more than domestic and agricultural use combined, and the anticipated growth of industrial consumption far outstrips that of domestic consumption, estimated 5x increase in industrial water consumption in the developed world by 2050. So Desalitech is focused on making that water available through a combination of treatment of unconventional water resources, namely salty water or wastewater, and doing so with a higher degree of efficiency, so getting more good water out of the water treated. So the process that I'll talk about offers these advantages. So operation at a higher recovery rate, recovery meaning the amount of good water extracted from the amount of water treated. Typically operating at 95% recovery compared to 75% recovery by conventional reverse osmosis methods. Not always possible, and I'll talk about that, but that's pretty typical for a project installation for us. With less energy and with increased reliability. And as a membrane process, what I mean by reliability is less fouling and scaling. And Desalitech systems operate flexibly. And what that means is that you can change most operating parameters at the control panel. Desalitech process is uniquely able to be adjusted. Cross-flow, flux, and recovery, the three main operating parameters for reverse osmosis, can all be changed, altered independently of each other in a Desalitech process. And I'll talk more about that when I have the process diagram in front of me. Okay. This is a curve, a chart published by Global Water Intelligence. It is the leading news and information resource for the desalination industry. And this is a little bit of a cynical thing. It's the curve of water technology. So you see the peak of the inflated expectations followed by the trough of disillusionment, the slope of enlightenment, and finally the plateau of productivity. So what you see on the plateau of productivity, the flat part extending to your right, is reverse osmosis, MED, MSF, established desalination technologies. And coming up on the slope of enlightenment is nano H2O and Desalitech at the top. So we like this chart partly because we're well placed on it, a lot of optimism about what we're doing. But I like to talk about it because what you see below Desalitech are mostly companies with orange spots on the curve. And what the orange means is that they're brine concentrator technologies, as opposed to general desalination or water treatment technologies. And I'll talk in the next slide about why there's so much interest in brine concentration. But on this slide, I'll say that almost all of those companies started out as general desalination companies, found that they couldn't compete with high-efficiency reverse osmosis, essentially resorted to brine concentration, more of a niche application than what they started out trying to do. This table shows the cost of ownership in terms of dollars per 1,000 gallons for a typical 10-year ownership period for a typical, I guess, large-size industrial desalination system. So what you see there is in the middle columns the typical RO system operates at 75% recovery. And what you see is that the capital cost amounts to about 3% of the total cost of ownership, energy, O&M, et cetera, on down the list here. By far the largest cost of ownership is the cost of brine and excess feed. So that's the water that the additional water that you're bringing in as feed and then discharging as concentrated waste from the back of the system. That's most of the cost of ownership. So if you're able to increase recovery, in this case from 75 to 93%, what you see is a 67% reduction in the total cost of ownership. So water efficiency matters a lot. And that is why in the previous slide I showed that so many companies interested in brine concentration. That's because reducing brine really pays. It saves a lot of money and reduces costs. This is basically the same information presented as a pie chart. This one is from Southern California Edison, a major power company in Southern California, and this is what they charted as their total cost of water. And by far the majority of it is the water. The rest of it is the operational costs and capital costs of water treatment systems. Desalitech is working with Coca-Cola. Got a couple of water purification systems in Asia, operating at 95% recovery from well water. We're also operating with a metal processing company in the middle of the USA. There we're treating wastewater and reducing the amount of water they need to haul off site. So these are two kind of extremes, both of them giving pretty short return on investment, and most of that is related to high recovery operation. We're working in the power industry, food and beverage, pulp and paper, oil and gas. In the upper right, that's a system that's at Tesla in California, the car company, cosmetics and consumer products. Okay, so that's a little bit of our resume. And with that, I'll dive into technology a bit here. So this is talking about reverse osmosis. I assume most of the audience is familiar with reverse osmosis, so I'll focus on cross-flow. But first, on the left, so RO works by essentially a salt filter. You apply pressure to salt water across a semi-permeable membrane. Fresh water flows through. You can't actually operate as shown on the left because salt tends to accumulate at the surface of the membrane quite rapidly. What's called concentration polarization. And it's a boundary layer of accumulated salt. So RO membranes are operated in cross-flow, and that's shown in the right. Permeate flows down while feed and brine flow to the right. So this is pretty much the way reverse osmosis membranes are operated everywhere. Nanofiltration is similar, and there's some kinds of ultrafiltration that are also cross-flow. The way that's configured in a traditional RO system is shown here. This is a two-stage traditional RO system with a high-pressure pump feeding a first stage. You typically only get about 50% recovery per stage. And that's because you need to leave some water in the feed and brine channel to sweep away the concentration polarization. So if you want 75% recovery, that's going to be 2 stages, etc. The other features here between stages are shown here: a pump, booster pump, and permeate throttling valves. Typically one or the other, and the purpose is to balance flux between the stages. There's too much pressure in the lead elements, and the salinity is very low, so you tend to get high flux in the lead elements right by the high pressure pump, unless you throttle permeate flow. And high flux can lead to fouling those lead elements. Meanwhile, at the tail elements, the last elements in the array, the concentration of salts is the highest, and so if you exceed saturation, you can get scaling, and sometimes there's insufficient cross flow in those tail elements. So this is typical reverse osmosis. We've learned as engineers to design and specify these systems as best as possible, but there's some sort of inherent limitations. This is simple filtration. So this is what you might see for a lot of microfiltration, but also cartridge filters and coffee filters, air filters, for example. All the water goes through. So you hold back the filtrate, whatever you're removing, and then periodically change the membranes, change the filters, flush the membranes, whatever. But the advantage this approach offers is that while you're operating, you're getting 100% recovery. So there's no brine stream. Just the amount of water that you pump ends up as permeate until, again, you either change the membranes or flush them. You can't do this with RO, though, because there's no crossflow. So what Desalitech has done is combined traditional reverse osmosis crossflow with simple filtration. So what you see here is a high-pressure pump feeding membrane array with brine recirculation. And it operates in two modes. One is in full recirculation mode, and the other is in a flush mode. So the full recirculation mode, the high-pressure pump is pumping, the circulation pump is moving the concentrate back to the membrane feed, permeate's being produced, and salt is accumulating as the retentate or the filtrate. And so you get an increase in osmotic pressure as recovery increases with time. You set the control panel to trigger a flush, and then at that point the brine flush valve opens and the high pressure pump pushes the concentrate out of the system with fresh feed water. And then the brine flush valve closes and you resume what we call closed circuit operation. So this is the reflex reverse osmosis process, semi-batch process. And we call it semi-batch because you never stop the pumps and you never stop producing permeate. So the flush happens on the fly. Okay, so some of the benefits of this approach are, one is that you've got good crossflow. Crossflow is supplied by that circulation pump. In fact, the only purpose of that circulation pump is to supply crossflow. So you can increase it or decrease it, and that varies your crossflow. Flux is determined by the flow rate of the high pressure pump. All the water that pump pumps in closed circuit operation comes out as permeate. So you can change that flux by turning that pump up or down with a VFD, variable frequency drive, without changing crossflow. And then finally, your recovery rate is determined by how frequently you trigger that brine flush valve. Recovery rate is independent of crossflow and flux. So you can circulate water and continue pumping permeate for as long as you like until you flush the system by opening that brine flush valve. And that's unique. So with a conventional RO system, there's a brine throttle valve. If you open that valve, you can increase crossflow, but it also decreases flux and recovery. Throttle that valve, you increase permeate production and recovery rate, but decrease crossflow. So these performance aspects are coupled in a conventional, traditional RO system. The independence of these has a big impact on system design and operation. Let's move ahead. Come back to this slide, no doubt. And I'll show you some case studies, some field data. This is one from a water reuse application. The water being treated here is tertiary effluent, basically sewage water coming from the back of a waste treatment plant. And the green and blue lines shown are from a Desalitech system operating on this wastewater over the course of about 90 days. And what you see is a decrease in normalized flux that's reversed by CIP, and then continued decrease of flux. This is very typical for municipal wastewater treatment with RO. The red line is for a traditional RO system operating at the same flux and recovery. And what you see is that flux basically crashes, and they couldn't recover it with CIP. So this shows that the Desalitech process, with its independently controllable crossflow and also short membrane arrays, has advantage of resisting fouling. I'll talk more about the short membrane arrays in a moment. So in this case, this is performance data from a system operating with a high silica feed. And it's an eye test. The chart's a bit hard to read, but the numbers shown on the data points there are the brine concentration of silica. We actually were able to get to about 930 milligrams per liter of silica in neutral pH, which is about 4 times saturation. The reason we're able to operate at such high concentrations and with this degree of supersaturation is that the system is flushed with new feed water before there's time for scaling to occur. So with any sparingly soluble salt, precipitation or scaling, there are 2 factors. One is you need to supersaturate, and the other is that you need to give the precipitant enough time to come out of solution. And that time is called induction time. It's a function of the concentration, the pH, the temperature, and a lot of other factors. But generally speaking, Desalitech systems supersaturate for less than the induction time for precipitation. That's how we're able to essentially trick silica to high supersaturations. That's similar good results with sulfates, calcium and barium sulfates, strontium sulfates. And we're still doing work on calcium carbonate and some other typical sparingly soluble salts, but silica performance is pretty outstanding. And now I'll talk about energy savings, and we'll get more into this when I'm talking about seawater RO. But the way it works is that a Desalitech system operates in recirculation. So the first recirculation is like the first stage of a multi-stage RO system. Second recirculation occurs at a higher pressure. Third recirculation at a higher pressure. And pressure builds over time. And so the operating pressure tends to be close to the osmotic pressure barrier or the osmotic pressure requirement of the water as it concentrates in the system. So it's a lot like a highly multi-staged traditional RO system in terms of energy consumption. But these systems are single stage. From a process control standpoint, what you're doing here is telling the high pressure pump to operate at a constant flow rate with variable pressure. So with a flow meter driving the VFD, the pressure of the pump increases as necessary to overcome the osmotic pressure. It's just enough to keep the flux constant. So the energy that you save then is essentially the area under the curve. You see a dotted line showing a single stage RO, and the staggered line of the CCD RO or the Desalitech system with much less of an average pressure requirement. I'll show some data for a seawater RO. It's just 20% less than state-of-the-art seawater RO in terms of energy consumption, and that if you're into seawater RO, is an enormous step change in energy performance. So this is a similar slide to what I showed before. It's a cost of ownership breakdown for seawater RO. What you see is by far the largest cost of ownership component is energy consumption. And this is a little bit of a different exercise. What we wanted to do here was say that, all right, if you pay 1% more in CapEx for a higher energy efficient system, basically that'll pay for itself if you're able to save 5% energy. Slightly different process used by Desalitech for seawater for brine concentration applications. You see the same arrangement in the upper part of the slide with brine recirculation. Then in the lower part of the slide is what we call a side conduit, basically a pressure vessel holding water that is used to exchange with the brine when you do the flush. So with this, we're able to operate without loss of brine pressure. It's basically retained in the system so that the brine leaves the system at atmospheric pressure. If this works, this will show the dynamics of that process. All right, looks like I'm not going to show this little movie here. It's all right, I'll move on. Actually, let me back up and talk about this slide a little bit. The pointer, apparently. See if I can use it in the diagram here. All right, so this is a multi-step operation, the way this process works. The first is with brine recirculation, as shown before. See here, I'm not as adept as I'd like to be with this tool. Okay, better. So brine recirculation. Then once you've achieved the recovery rate set point, the valve shown here opens. Water pushes down into the side conduit, pushes fresh water into the RO system, and the brine drops down into the side conduit. These valves isolate, and then the side conduit is flushed at low pressure while the membrane system continues to desalinate. Move on. All right, so here's some performance data for operation in seawater RO. We measured 1.9 kilowatt hours per cubic meter, but this was in cold water, 15 degrees C water at 47% recovery. So if you normalize that to standard seawater temperature that's used for comparison, that drops the specific energy to below 1.5 kilowatt hours per cubic meter, which compares favorably to 2.2 to 3 kilowatt hours per cubic meter in large state-of-the-art seawater RO plants. I mentioned that I come back to membrane arrays. And I'll do this in the context of high permeability membranes. So what's shown on the left here is the flux distribution for low permeability membranes. The x-axis is position in the pressure vessel, the membrane array, and the y-axis is flux in LMH. The left then is the lead element. So what you see is high flux in the lead element, lower flux in the tail element. The red line is for a 7-element array. and the blue line is for a 4-element array. So just by having a shorter membrane array, you get a better flux distribution, meaning it's a lower lead element flux and a higher tail element flux, better flux distribution. So shown on the right, if you're using high permeability membranes, that difference is exaggerated. So the lead element flux is even higher, the tail element flux is even lower, but there's some advantage in using a shorter membrane array. And that's typical for a Desalitech system. We're using a 4-element array. You don't need as many membranes in series because you're achieving recovery by recirculating. You don't get more recovery by putting more membranes in a line. So what this enables is use of high permeability membranes in Desalitech systems. If you're using high permeability membranes in a traditional RO system, a lot of times you need to do internal staging. So you need to put high rejection membranes in the lead element positions, thereby pushing flux to the back of the membrane array. You don't have to do that internal staging with the Desalitech system, and that gives you an overall energy benefit. You get the full benefit of a high permeability membrane. So I'll summarize. Use of unconventional water resources and doing so at a higher efficiency is inevitable. That's where we're going everywhere on the planet. What Desalitech is offering is a higher recovery rate, lower energy consumption, and better reliability, flexibility, by resisting fouling and scaling. We are going to market with standard products, 50 to 1200 GPM. We're already working with a number of Fortune 500 companies and other global water treatment firms. And we are headquartered. We are manufacturing now in the USA, although we're working with partners everywhere, including Malaysia, in your part of the world. All right, with that, I look forward to your questions.
Thank you so much, Rick. Really informative presentation. If anyone would like to ask any questions, we still have Rick on the line. So if you'd like to type your questions into the text box at the bottom left-hand corner, I'm sure he will answer them as best as he can.
So question is, what's the cycle time for brackish water RO? It really depends. It's flexible, but typical from a design standpoint is somewhere between 6 and 30 minutes. So a higher recovery operation will operate with more recirculation cycles and have a higher overall sequence time. But if you have sparingly soluble salts in the system, they'll tend to concentrate up over time and finally be supersaturated only in the last few recirculations. Waiting for a question. Great, thank you. Explain a bit more. How do we control the saturation limits of salts in order to perform CIP at the right duration? This is still a work in progress as far as monitoring, scaling, and triggering CIP at the right time. The typical way you do it in a Desalitech system is similar to how you do it in a conventional RO system, which is to monitor normalized flux. So you track pressure and flow and temperature, water temperature, and then you trend that over time. And when you see a reduction in normalized flux, you know that there's something going on in your system. It's a little dangerous with scaling. Sometimes you can have irreversible scaling if you supersaturate. So you need to track that carefully and understand the chemistry of your system. But at the end of the day, you can't. You know, the only standard means to track scaling is to look for a change in flux. So that, again, it's the same with the Desalitech system. You can pilot, you can do jar studies and some other things. We get a lot of cooperation from the anti-scalant manufacturers in terms of water analysis and system diagnosis. Now, in terms of designing a system and operating it, it's good to do a water analysis and understand the chemistry. Okay, so another question is, have we considered energy recovery? The way a Desalitech system works, it discharges brine at atmospheric pressure. So there's no energy in the brine discharge stream to recover. And you know, unfortunately, it's a little difficult to illustrate that with the tools that I have here. But I'd invite you to visit Desalitech's website. There's some animations and some other illustrations there that show how the Seawater RO system works with the side conduit. But the answer to whether an energy recovery device can be used or not, I would love it if we could use one, but it doesn't work from a work process standpoint. And anyway, the system operates at a level of efficiency without discharging high concentrated brine. It doesn't need it. All right. So, reading questions here. All right. So, is the recirculation pump putting heat into the system? Is anti-scalant dosing incorporated at high concentration in the system? So, the way the system operates is that it recirculates for a period of time while the salts concentrate in the recirculation loop. Periodically, the brine is released. But all the while that it's concentrating, there's new feed water coming into the system. So we really see little or no increase in heat in the system with time because there's not that much time. But also the amount of energy that the recirculation pump is injecting is pretty minimal. It's just applying enough pressure to keep the water moving. It's not actually pressurizing the water. I'm going to switch my camera off. Turn my microphone on. Hopefully this will keep the system fast. Okay, so no, we don't see heat increase associated with the recirculation. And then dosing. Dosing is done in the same way in our system as in a traditional RO system. You do it with the feed at a steady rate. It increases in the system over time, just like in a traditional RO system. Concentration increases as you go down the line of membranes, ultimately getting to the concentration that you need in the brine. Okay. Another question, two questions. How do membrane replacement frequencies compare to conventional RO? Membrane life is the biggest variable or biggest factor in membrane life is the cleaning frequency. So the more often you have to clean your membranes, the shorter their life is going to be. So by resisting fouling and scaling, Desalitech systems tend to reduce CIP frequency, and that contributes to membrane life. That said, most of our customers are pushing our systems to high recovery rates. And the reason is because the cost of membrane replacement is less than the cost of wasted water. So it's worth it to them to replace membranes at the frequency that you would do so with a typical RO system. but get a higher recovery rate in the meantime. And then the second question, is it possible to retrofit an existing plant? It is. In fact, a number of our installations are retrofits. That's because Desalitech systems are comprised of off-the-shelf reverse osmosis equipment, membranes, pressure vessels, piping, all of that. It's just standard stuff. All we're doing is putting it into a new configuration. However, we do like the short membrane arrays of 4 elements for the reasons I've outlined. And if your existing RO system has 6 or 7 elements, the retrofit might be pretty substantial. You might be needing to add racking and pressure vessels. It really depends. And sometimes the amount of field work required in adapting the existing equipment to the new application is enough to make it that it's not really worth it. So we'll typically go in, do the assessment for a retrofit, and also offer a new system proposal. And then often our customers will say that, well, if I buy a new system, I can keep my old system running until the new system comes online, and then look at shutting down the old system and retrofitting. So another question similar, is it primarily for new builds, or is it able to retrofit an existing operation? Again, we can do retrofits, but most times we're doing new builds. And, another consideration is if you've got an existing system and an old system, chances are it's got old membranes, old instruments, so the opportunity to achieve higher efficiency with a newer system is a lot of times it's just worth it. So another question, what's the largest seawater plant that we've constructed, and what was its recovery rate? Well, recovery rate in seawater RO usually isn't as much of a driver. The sea is essentially infinite, so there's a cost associated with pretreatment, of course, but in terms of brine disposal, usually you just let it go back to the sea, and it's not expensive. So recovery rate isn't usually a driver in seawater RO. In fact, if you go to high recovery, there's going to be an energy penalty associated with doing so. So the biggest cost of ownership in seawater RO is energy consumption. So typically the high efficiency energy performance is most critical. We do not do a lot of work in seawater. We've got a couple of our longer running plants are in seawater. Most of our work is in brackish and industrial water. And the reason is, for seawater we offer lower energy consumption. It's important, but that's really most of what we bring there. For brackish and industrial water, we offer low energy, but also high recovery, fouling and scaling resistance, flexibility, etc. So that's where most of our market is and what we've been pursuing. So what is the recirculation percentage of the total flow? It really depends. So with low TDS water, we can get about 40 to 50% recovery per recirculation. So like a 95% recovery operation would be something like 12 recirculations. In seawater, you need to go at a lower recovery rate. So we'll do about 20 to 25% recovery per recirculation. So typical 45% recovery seawater operation will be about 3 recirculations to achieve that. Depends on the TDS. All right, how much free volume is upstream of the membranes? For 6 membranes in an 8-inch vessel, there's about 3,000 liters. It's half filled with membranes, only 150 liters are free, about 1 minute of residence time. Okay, so what this is talking about is that's right. So for a brackish system, we can fill the pressure vessel with membrane elements. For a seawater system, we need to leave some empty spaces in the pressure vessel. And what that empty space does, or that additional volume does, is give us a little more recirculation time before we need to flush the brine out of the system. So typical seawater installation will be 4 elements in a 7M vessel. So it'll be 3 empty spaces. We usually put them in the head of the vessel. The cross flow tends to push the membranes to the back of the vessel. So we can do that without a spacer. And then we're getting on the order of 6 minutes of recirculation time before we need to. So part of the way we're able to do that is we operate at relatively low recovery per recirculation. I don't know if that answers the question. Yeah, some back of the envelope numbers here. I think I answered the question though with the amount of space we leave in the vessels. All right, so another question. Are membranes custom made or are they typical? We're only using standard membrane elements. So off-the-shelf standard membrane elements. And we get about the same performance you do with traditional RO in terms of salt passage and permeate composition. In fact, we do our design and modeling with standard membrane projection tools, your ROSA or IMS Design or ADS, T Plus, or any of these. So we're just doing multiple iterations. So you do it like do an initial projection with your first recirculation, and then another projection with your last recirculation. Combine those results together in a spreadsheet to get the outcome, which is typically pretty accurate. So the field test results match up with the projection results, and we have the full backing of all the major membrane companies in terms of their performance guarantees apply. So if the membrane projection says you're going to get 200 parts per million TDS, the membrane manufacturers will stand behind that performance with membranes used in a Desalitech system. I will make this presentation available, no problem. I'll send it to AWA. In fact, they have it already. Free to distribute it. So another question, do we see similar benefits with biofouling as we get with scaling? It's a little bit different. With biofouling, I showed the operation in wastewater where the traditional RO system fouled up pretty quickly. Conventional RO system the Desalitech RO system was, not only sustained flux for longer, but was able to cleaned up better for CIP. What's going on there is that we've got good cross flow in the system and good flux distribution. So the short membrane array prevents the lead element from overfluxing. The high cross flow similarly keeps the lead elements from overfluxing, keeps good cross flow. So those are the main means to resist fouling. With scaling, the mechanism is a little bit different. I talked about it a little bit when I talked about silica. The mechanism there is cross flow sure helps, but the thing we're working with is that the cycle time is short, so that the amount of time you're in supersaturation is limited, and sparingly soluble flushed out of the system before they get a chance to come out of solution. All right, I believe I've gotten through all the questions. And I think we've gotten through about the allocated time here. Are there any questions from the moderators or anyone else?
We've got a couple of people in the room here. Does anyone have any questions? Just 2 seconds, Rick.
What areas of the fouling process of the membrane do you see that can be improved? If we're going to start introducing this kind of technology to larger scale desalination plant, what needs to be achieved in that environment?
So I didn't really hear you very well. You talked about fouling resistance in large-scale desalination plants.
Yeah, applying this technology to that environment.
Right. Well, there's some inherent limitations with RO. RO uses a hydrophobic membrane. It tends to foul with organics in the water. This is one of the disadvantages with the thin film composite polyamide polysulfone membrane chemistry is that it increased the requirements for pretreatment compared to the original cellulose acetate, which is a hydrophilic membrane, tends to coat with water and resist fouling, and in fact resist chlorine attack better. But the advantages with the TFC polyamide polysulfone are better flux, lower cost fabrication, less defects in the membrane, makes it worth it to do the pretreatment you need to do. So since Desalitech is using off-the-shelf membranes, basically you've got the same, use the same precautions in terms of limiting the amount of COD, TOC being fed to the membranes. Certainly want to remove oil and grease. You need to make sure there's no free chlorine in the feed water, that it's very, very limited, etc. So these are the precautions you need to apply to any RO system for the sake of fouling resistance and membrane life. In terms of scale, reverse osmosis is a very scalable technology. So if you go to the Perth plant or Sydney plant or any of the big RO plants, most of them are all 8-inch membrane elements, and you're not going to a much larger membrane size for a bigger plant. You're just using more standard elements. I guess we've all heard about the 16-inch membrane elements. Again, it's a step up in size, but still, the way you achieve volume and capacity is with more of them in parallel. So it's the same with the Desalitech system. You just plug more of them in parallel and still drive a train with a single pump. So it's a very scalable technology.
Okay, if there aren't any more questions, I'd like to thank Rick on behalf of the Australian Water Association for your time. A really great presentation, and the slides and this presentation, the recording, will be available. I'll probably have it sent out to everybody by the end of the week. And yeah, so thank you very much for attending, everybody, and thank you, Rick, and we'll leave it there.
Oh, great one. Who's the best one to go?